Okay, so in the previous video, we talked about continuity, and we ended with looking at some different types of discontinuities that can occur in a function. What we're going to do now is start to introduce the idea of continuity on an interval. So our definition of continuity was concerning, what it means for a function to be continuous at a single value. So up here, for example, let's take this part B, this removable discontinuity. This graph is the graph of a line with a hole in it and a point defined elsewhere. This function I could say is not continuous, but if I want to be a bit more specific, I could say that it is continuous at certain values. So for example, at 1, I could see that there is a point on this line where the value, if I'm calling this function f of 1 would be equal to the limit of f of x as x approaches 1. I can just see that visually from the graph. So this function, even though it has a discontinuity at 2, it's continuous at other values. And that's what our definition of continuity allowed for, checking for continuity at one specific place at a time. One specific number at a time, I should say. To lead into the definition of continuity on an interval, we start with this definition. What does it mean for a function to be continuous from the right at a number a, and then similarly continuous from the left? So, so we have this, if we have a function f that's continuous from the right, what that means is that the limit as x approaches a from the right of f of x is equal to f of a. Compare that to our definition of continuity that we gave in the previous video, which was basically the same thing, except this was a two-sided limit. There wasn't a from the right condition on this thing. So this is almost identical to our definition of continuity, but we're only requiring the right-hand limit of f of x equal f of a. Similarly, if f is continuous from the left at a, that's the same thing as saying this. The limit as x approaches a from the left of f of x is equal to f of a. And we'll show in the next example why we might need this kind of definition for continuity from the right or the left. But now that we have this, we can talk about continuity on an interval. So we say that a function f is continuous on an interval if it's continuous at every number in the interval. Now remember, an interval is a set of real numbers. And down here in this example, you can see I have an example of a closed interval. This represents a set of real numbers. It's the set of all real numbers between -4 and +4, including those endpoints -4 and +4. So we say that a function is continuous on an interval if for every single number within this interval, we can say that the function is continuous at that number. Now, if this interval is a closed interval, like the one that we have here, then continuity on the interval, we have to be careful with that when we're dealing with the endpoints, as we're going to see from this example. So continuity on an interval is a little bit more involved than what we just said. It's not just that it's continuous at every number in that interval, but if we're looking at the right endpoint of that interval, we only need the function to be continuous from the left, because we only know that we can use values within the interval to approach that. So 4 in this case. We don't know if the function is even defined past that interval, so we can't necessarily approach from the right. So continuity on an interval, when we're looking at the endpoints in particular, we only require the function to be continuous from the left when we're looking at the right endpoint, and from the right when we're looking at the left endpoint. So let me illustrate that with this example. Okay, show that f of x equals the square root of 16 minus x squared is continuous on this interval. Now there's a couple of ways we can go about this, but I think the best way is going to be looking at a graph. And this is a very, very important type of graph for you to recognize. So this guy, if you're not familiar with what this is the graph, or what the graph of this looks like, I'm going to rewrite my function using y. Y equals the square root of 16 minus x squared. Okay, if I were to square both sides, y squared equals 16 minus x squared, and then add the x squared over, I would get this. Now you should recognize this as the equation of a circle centered at the origin with a radius of 4. Square root of 16 is 4. But the graph of this will not be a circle. If it were, then we wouldn't be looking at a function at all, because a circle would fail the vertical line test. In fact, what we are looking at is a semicircle, which I did not draw perfectly well. Mine's a little bit too long horizontally, but this should look like a semicircle. How do I know that it's a semicircle, not a full circle? Well, if I were to work these steps backwards, subtract x squared over here, take square roots of both sides to get up to this step. Anytime you take square roots of both sides of an equation, one side should be picking up a plus or minus. Notice how we don't have a plus or minus here? Because we were given only this positive square root of 16 minus x squared to begin with. If y is equal to the positive square root, then that means that I'm looking at the circle that lies above the x-axis, not below it. So this would be the graph of a semicircle. This function is not defined outside of the interval -4 to 4. And you can verify that pretty easily. If you pick any number greater than 4 or less than -4, then squaring that value will give you something larger than 16. So that 16 minus that is negative. Square root won't be defined in that case. Now looking at the graph, I can see that I was able to draw this semicircle without picking up my pen at all. So we do have continuity within that interval. And why, again, why was it important that we only require continuity from the left when looking at my right endpoint? Well, if I'm looking at continuity at the number 4, notice this function, because it's not defined to the right of 4, I can only approach 4 from the left. I can't approach it from the right. So if continuity on an interval required the limit as x approached 4, for example, to equal f of 4, then I wouldn't have continuity there because the two-sided limit doesn't exist, but the left-hand limit does. So similarly, I can approach -4 from the right, which is why continuity from the right is necessary, is all that's necessary of my left endpoint. Okay. I could have also evaluated those limits algebraically, but I chose to use the graph just to show that there's value in using the graphs as well in dealing with limits. So let's come up here. This next theorem talks about how we can construct continuous functions out of other continuous functions. So it says if f and g are continuous at a, and if c is any constant, then the following functions are also guaranteed to be continuous at a. So f plus g, f minus g, that constant times f, f times g, f over g, as long as the number that we're continuous at, g of a, is not equal to 0, because then this would be undefined. We don't need to prove these because all of the proofs follow directly from the limit laws that we talked about in 2.3. Remember, the definition of continuity involves a limit. And so any proof of a theorem involving continuity would naturally involve results that we have for limits. And exactly those limit laws that we talked about would lead to all of these results. So we're not going to go through and take time to prove this stuff. But this is really useful because it shows us how to construct new continuous functions out of old ones. Okay. One additional thing, so we've talked about continuity at a number a, we've talked about continuity on an interval. If a function has a domain of all real numbers, so a function is defined everywhere, and if that function happens to be continuous everywhere, so everywhere on its domain, then that's the terminology that we would use. I could say that a function is continuous everywhere, or sometimes we simply say that the function is continuous without specifying where. That implies that the function is continuous at every real number, and we may use either of these two symbols to denote that. This kind of fancy capital R is the symbol that we use for the set of real numbers, and this is the interval from -infinity to infinity, also representing the entire real line. If a function is continuous everywhere that it's defined, then we say that it's continuous on its domain. So this would concern functions that are that might be defined on all real numbers, or maybe they have some places where it's not defined, but everywhere that the function happens to be defined, if it's also continuous, then we would say this. It's continuous on its domain. Okay? This next theorem shows us that certain very common functions are continuous everywhere on their domain. Polynomials are continuous everywhere. They're defined everywhere, so that's also the same thing as saying that they're continuous on their domain. Rational functions are continuous on their domain as well. Rational functions are not necessarily defined everywhere because rational functions involve a denominator, and sometimes for some values of x or whatever your independent variable is, your denominator can come out to 0. You may have vertical asymptotes or holes in the graph or things like that. So, but those would be values that are not in the domain of the function. For all values that are in the domain of said function, the function would be continuous there as well. That's what this theorem is saying. There's a proof down here of the first part of this, and then part B would follow directly from part A and number 5 up here from this previous theorem, because a rational function is a quotient of polynomials. So this follows pretty directly. We can walk through this proof really quickly. So again, the goal here is to prove that a polynomial is continuous everywhere. So we can define kind of a general polynomial here. P of x equals this expression, cn minus 1. All of these c's represent coefficients, and then x to the nth power, x to the n minus 1, so on and so forth. So it's some general nth degree polynomial. We know from our limit laws, it's denoting them here by law 8 and law 10 and all this kind of stuff. So we're talking about our limit laws, that the limit as x approaches a, where a can be anything, of some constant c naught is always equal to that constant c naught. We also know that the limit as x approaches a of x to the m for any positive integer m is equal to a to the m. We can use direct substitution there. Okay? And so they give kind of this argument here, but basically what it's saying is if you're using the definition of continuity, which continuity at some general number a, we would be taking the limit of this polynomial as x approaches a. But these laws here, these facts, are enough to justify that evaluating that limit is the same thing as using direct substitution, plugging a directly into all of the x's here. But that would be the same thing as p of a, which is confirming continuity for us. Okay? So moving on from there, the definition of continuity, this is really, really important. The definition of continuity implies that the limit of a function f as x approaches a can be evaluated by direct substitution anytime f is continuous at a. And again, the reason for that goes right back to the definition. So I'm going to reference this again. When we know that a function is continuous at some value a, by definition, what that means is that the limit as x approaches a of f of x equals f of a, meaning I can plug a directly into this function to evaluate this limit. That's really, really useful when we can use that. So for example, let's evaluate the limit as x approaches 2 of x squared plus 3 over x minus 1. Normally, I'd have to do this big long argument using limit laws and things like that. However, we know that this is a rational function. And according to this theorem that we just talked about, rational functions are guaranteed to be continuous anywhere that they are defined. So, is this rational function defined at 2? Well, yes, it is, because the only place that we have to look to find out where a rational function is not defined is the denominator. And I can see from this that the only place where this function is not going to be defined would be when x is equal to 1. There's no issue when x is equal to 2. So because it's rational and because we know that this function is defined at 2, that theorem tells me that it's also continuous at 2, which means that this limit can be evaluated by simply plugging 2 into my x's here. 2 squared plus 3 over 2 minus 1, which is equal to 7. Very straightforward. Plugging something in. Okay? It turns out that there are lots and lots of familiar functions that are continuous everywhere on their domain. Here's a list of them. This is going to account for potentially all the functions that you even know about. And this shouldn't come as a huge surprise because prior to this class, whether in trigonometry or college algebra, or if you ever took a pre-calculus course, something like that, you would have seen the graphs of all of these. You've graphed polynomials, you've graphed rational functions, root functions, square root, cube root, things like that, inverse trig, logarithmic functions, exponential functions, trigonometric, I can't remember if I said that already. You have seen the graphs of all of these, and you can confirm from when you learned about those graphs that they are continuous everywhere that you would be, everywhere that those functions are defined. Now, I want to be careful with that because I'm not saying that these functions are continuous everywhere. Take, for example, the tangent function, right? So the tangent function has an infinite number of vertical asymptotes, like that, right? This is obviously a very, very rough sketch, but this is roughly what the tangent function looks like. There's infinite copies of this thing. The fact that this has vertical asymptotes is not contradicting what this says, because this does not say that these functions are continuous everywhere. Some of them are, polynomials for example, but many of them are not. It's saying that they are continuous on their domains. So everywhere that we have a vertical asymptote in your tangent function, that whatever number that occurs at, that's not part of the domain of tangent, because tangent's not even defined there. But if you look at everywhere that the tangent function is defined, we have continuity at all of those points, okay? So let's look at more complicated functions. Where is this function? I should actually write it as f of x equals, so we know that we're looking at a function, but where is the function f of x equals natural log of x minus arcsine of x all over x squared minus 1 continuous? Well, each one of these, logarithm, inverse trig, polynomial, they're all a part of this this listing of different types of functions. So by themselves, each one of those functions is continuous everywhere on its domain. In addition to that, according to this theorem back here, anytime we add, subtract, multiply, divide, or multiply by a constant functions that are continuous, the result is also continuous. With the quotient case, we have to look out for when that function gives me a 0 in the denominator. So that tells me that if I can find where all three of these functions are simultaneously continuous, then anywhere those values are also going to be where this more complicated function is continuous, except for anywhere that my denominator is equal to 0. So let's look at the domain of the natural log first of all. The domain of y equals the natural log of x. So we know from algebra that the domain of any logarithm function, natural log included, is the set of all positive numbers, okay? 0 to infinity. Where is the domain of arcsine? Domain of arcsine. Arcsine is defined on the closed interval -1 to +1. Okay, so we'll get to the denominator of this thing in a second. But if I were to create a number line, -1, 0, 1, 2, -2, so on and so forth, then what I'm seeing is that the domain of my natural log function is all of that, right? And I'm also seeing that the domain of my arcsine function is all of that, okay? In order for this function to be defined at some number a, I need to be able to plug a into all of the x's that appear in this function, which means any number a that I plug in has to be defined at all functions simultaneously. So I'm basically looking at where these two domains overlap, and they overlap on this interval from 0 to 1, but I can't include 0 because my natural log function is not defined there. So this is the interval 0 to 1, and it's a half open interval because it includes 1. But now we need to look at our domain, or denominator down here. This denominator is equal to 0 when x is equal to plus or minus 1. So that actually rules out this right endpoint of 1 here, because if I tried to plug 1 into this function, I would be dividing by 0. We have to remove the 1 from this set, which means now we're looking at the open interval from 0 to 1. But this would be the interval on which this function is continuous using the theorems that we just talked about. Here's one more example, and then we'll stop this video and move on to the third video, which will wrap up this section. It's another limit, okay? This time the limit involves it's a rational function, or it's a quotient, I should say, involving some trigonometric functions. And again, remember, this theorem tells us that trigonometric functions are continuous everywhere on their domains, and then that previous theorem says that when we combine continuous functions the way that we are here using division and addition and stuff like that, the result is also continuous. So this thing is, if pi over 4 is in the domain of all of these functions here, and it's not going to cause me to divide by 0, then this function is continuous at pi over 4, which means my limit can be evaluated just by plugging pi over 4 directly into this. And we know, just from our knowledge of trigonometric functions, that tangent is defined at pi over 4, as is the sine function, and it's very easy to see that sine of x plus 3 is not going to equal 0 for pi over 4, nor will it equal 0 for any value of x, which hopefully you can verify why that's the case. So I can evaluate this by plugging in pi over 4 directly. Tangent of pi over 4 over sine of pi over 4 plus 3. Tangent of pi over 4 is equal to 1. Sine of pi over 4 is root 2 over 2 plus 3, and I don't like having the complex fraction here, so I do prefer to multiply by 2 over 2, same as multiplying by 1, because that 2 is going to cancel that denominator. This gives me 2 over root 2 plus 6, okay? I'm going to go ahead and keep my answer that way. This might bother you a little bit, depending on who your algebra teacher was, or trigonometry, because there's a radical appearing in the denominator. I'm just going to mention this once to get it out there. Before calculus, we make a lot of instructors will make a pretty big deal about rationalizing a denominator. I actually make a big deal about it when I teach trigonometry, because when you rationalize denominators, it reveals some interesting patterns with your sine and cosine functions. But beyond that, there's not actually many good reasons to rationalize denominators. And you'll see in calculus and above, we tend to not bother. We tend to just leave radicals in the denominator. So you don't need to rationalize this, but I do like to eliminate any smaller fractions that are appearing in an answer like this. Okay, so I'm going to go ahead and cut this video off here, and we can finish up in the next one.